Software development for real-time embedded systems. Project 9.
Welcome to the Project 9 demo. I'm Daniel, and Brad will be our pilot as we show off our quadcopter-mounted IMU module capturing roll, pitch, and yaw, transmitting values over I2C to an Arduino Uno, which formats and reports the results in degrees to a Raspberry Pi over USB, and ultimately transfers the IMU data to my host machine via Bluetooth. The hardware layout is identical to Project 8, KK controller quadcopter design carrying a 5V battery pack powering a Raspberry Pi 4, Arduino Uno, and Adafruit absolute orientation sensor tied to the front. The key difference is the reliance on Bluetooth as a wireless transport layer rather than a 2.4 GHz Wi-Fi signal. The Arduino RTOS sketch is identical to Project 8 with the slight exception of formatting in the output text to facilitate cleaner packing of data into the Bluetooth serial port. The Arduino sketch configures the I2C serial connection, defines a real-time task that reads in values from the Adafruit peripheral, and parses and sends results over serial output. The task reads orientation data from the Adafruit roughly every 250 milliseconds. The background of the video is my Windows 10 desktop, but I have an Ubuntu VM loaded through VirtualBox to make the host connection a little cleaner. Overlaid on the left will be a synchronized iPhone video of the drone. We start with the Ubuntu VM already loaded, and I'm bringing up PuTTY to SSH into the Raspberry Pi over Wi-Fi, but this is just to facilitate the connection and sending of data. After logging in, I run HCI config, which allows me to see the Bluetooth MAC address, which I'll be referencing later. And I do the same on my VM. I was able to forward the Bluetooth from my desktop into the VM, and this will serve as the host server for this connection. The server code is here in Python. It defines the host MAC address, which is a local Windows Bluetooth dongle. The port 5, is arbitrary, but the client and server must match on that. I connect the socket, bind and listen over it, and wait for the client to connect and send data, at which point I simply print it out to the terminal. Opening a Bluetooth control, I see the local controller, and later we'll see once the Pi connects. I start up the server on another terminal inside Ubuntu. And just to show the Arduino is forwarding the data from the Adafruit sensor, I cat into the ACM0 device, and it's updating as expected. Here I bind RFCOM0 to the MAC address of my desktop on port 5 to match the server, which allows me to send data from the Raspberry Pi, which I'll do right here, a simple cat, and forwarding the information into the RFCOM0 serial port, which will send over Bluetooth, and we can see it connects automatically to the desktop because they're both already trusted. And Bluetooth control shows me the Raspberry Pi information that we are connected, paired, and that's the device ID that I saw earlier. Now, over on the outside on the patio, we see Brad first manually controlling roll, pitch, and yaw. And you can see the corresponding values shifting around on the terminal side. Now he's walking over to start actually flying this bad boy. Flying in quotation marks. And we see the roll, pitch, and yaw are static while the thing's not moving. That's always a good sign. But as soon as it starts wiggling around, we get a lot of slight variations. It's not doing any significant loop-de-loops here, but we can see that the orientation sensor is getting data and sending it, and we're receiving it over Bluetooth onto our host machine. And the remainder of the video is essentially just more of this. So feel free to stick around and watch if you want to see a wiggly quadcopter. But otherwise, thank you for watching. Only one more project left.